So now returning to our multivariate Gaussian example, again using the flowchart and the block language that's going to be isolated to this particular lecture, we have in block 2 that we've defined a multivariate Gaussian model for our data. We've said that we have data points x1 through xn. Each of these data points is in Rd. We are going to assume that they're IID from a multivariate Gaussian, meaning that each of these data points is an independent experiment, an independent trial, where we get a random vector from a multivariate Gaussian with a mean mu, which is a vector in Rd, and covariance sigma, which is a d by d matrix that's positive definite. We've defined this model, but we don't know the mean or the covariance. So really we've defined a family of distributions. We've defined the family of multivariate Gaussian distributions for our data with an IID assumption. So that's our block 2 problem. With block 3 now, we've defined that we want to find a value for mu and sigma that maximizes the joint likelihood of our data. So we've defined the joint likelihood of our data as the function that we want to maximize. In this case, it's maximizing the function because we want it to be more probable, our data set to be more probable. In other cases, we'll want to minimize a function usually when we have no probabilistic interpretation. So we've said that now we want to find a value for mu and sigma, and the value that we want to find is the one that maximizes the log of the joint likelihood, which has this form, the sum over the log of the individual likelihoods. And the value that maximizes this function is the value of mu and sigma such that the gradient at that point is equal to 0. So to finally solve block 3, to find the value of these parameters for our model, we have to now take derivatives. So here's how we're going to do that. So again, we want the final gradient to be equal to 0, so we'll put a 0 here. First, let's take a derivative with respect to mu. And so the way that we're going to now take these derivatives is simply unique to this problem. Other problems we might do the derivatives in a different way or in a different ordering. Right now I'm simply focusing on the derivative with respect to mu and ignoring the derivative with respect to sigma. And it's going to work out in that case. So we have the log of the joint likelihood. That is the sum of over each of the n observations of the log of the multivariate Gaussian evaluated at each observation. So here we're starting to get into the actual math where we're plugging things in and solving math equations. So we write out the multivariate Gaussian density function. We evaluate it at each of the n data points for particular mu and sigma. We get this. We can now take this log and simplify it in this way. So we've simply written the log of this product of two terms as the sum of the log of each of those two terms, and we get this function. And now we take the derivative of this function with respect to mu, and we find that we get this term here. So this term here is the gradient of the log of the joint likelihood with respect to the mean vector mu, and we want to set this to 0. So notice that we don't actually set it to the scalar 0 because this is a d-dimensional vector. We're actually going to set it to a vector of d zeros in this case. So that's one thing that we need to note. Okay, so now let's see if we can solve this. And so we simply do it by inspection, and we notice that fortunately sigma doesn't matter. For any value of sigma, we can find the optimal value of mu by setting it equal to the empirical average of all of our data points. So if we set mu to be equal to the sum over all of the data points divided by n, the empirical average, call that the maximum likelihood value for mu, then that is the value at which this function this function here is equal to 0 for any value of sigma. So fortunately, it turns out in this case that sigma does not change our maximum likelihood solution for mu, which is why we could simply solve mu first. We now need to find the maximum likelihood solution for the parameter sigma of our multivariate Gaussian. So we perform the same exact steps as on the previous slide, with the exception that we're now taking the gradient of the log of the joint likelihood with respect to the matrix sigma and setting that gradient equal to a matrix of zeros. So again, because sigma is a d by d matrix, when we take the gradient of this function with respect to that matrix, what we get is not a scalar 0. Often we just write 0, even if we're not talking about a scalar value. We get a matrix of zeros. That's a d by d matrix of zeros. So we have our log of our joint likelihood. We take the gradient of that with respect to sigma, and we get this function here. This is a d by d matrix. Notice that it's a function of mu, and it's a function of sigma, and we want to find the value of sigma and mu such that this is equal to a matrix of zeros. So we already know mu. We know that mu is optimized at the point mu ml here from the previous slide. So we know that we're going to evaluate this thing at the point mu ml from the previous slide. And so solving then for sigma by setting this term equal to the matrix of zeros, we find that sigma, the maximum likelihood value for the matrix sigma, is simply equal to the empirical average of the outer products of our data where we've subtracted off the maximum likelihood mean. So that's the solution for performing maximum likelihood of the multivariate Gaussian distribution using an IID assumption. So to again summarize, if we have n observations, so this is the data, block 1, each of those is in RD, and we then want to transition to block 2. We want to define a model for it, so we hypothesize that the data was generated IID from a multivariate Gaussian, so we've defined the model. We now need to figure out how to set the parameters of that multivariate Gaussian, so that then motivates block 3, which is the inference portion, where we define the objective that we want to optimize to be the likelihood function. So we want to find the value of the parameters of a multivariate Gaussian that maximizes the likelihood, and then derive an algorithm for doing that. And when we followed through on that process, we found that the maximum likelihood solution for the Gaussian was to set the mean equal to the empirical average of the data, and to set the covariance equal to the empirical covariance of the data, where we subtract off the maximum likelihood mean. So we've solved the problem, and now the question is, are we done? So obviously we're not done. There are many assumptions and issues with this approach that makes finding the quote-unquote best parameters not a complete victory. So again, we made a model assumption. We assumed that the data was IID, independent and identically distributed as a multivariate Gaussian. This was an assumption that we made that might not be true. For example, we might think that there's sequential information in these vectors, that the vector, the ith vector in this sequence, depends somehow on the previous vector in that sequence. This model does not make that assumption, because that would violate the IID assumption. So we've made a modeling assumption, block 2. We made an IID assumption. Then in block 3, we defined an objective that said what the best value of the parameters are. This also was an assumption. What it means to say that one parameter setting is better than another depends on what function that we define that we want to optimize, which is a choice that we also make. So the choice of objective function was also arbitrary on our part. Once we made that choice, then the actual algorithm that we followed by taking derivatives was optimal. We solved the problem, but that problem was solved for a function that we chose, that we made an assumption was a good function to model the data. So in many cases, perhaps we don't want to maximize the likelihood. So for example, we haven't been talking about block 4. Here's where block 4 would come into play. We often want to use the maximum likelihood solution. So for example, we would want to use the mean and covariance of our multivariate Gaussian to make predictions about a new value that we haven't observed yet. To say, here's where I think, here's the region of the space that I think the next value is going to come in. And also, here's the region that I don't think the next value will fall in. So how does the maximum likelihood generalize to this new data point? And so we'll discuss a little bit in future lectures about this. However, at a high level, if the data that we're modeling, x1 through xn, if that data doesn't somehow represent our space or capture our space well, if it doesn't cover everything that we can expect to see, if there are huge gaps that are missing in our data, then the maximum likelihood solution can overfit. It'll only learn based on what you give it, and it's not going to have any sort of way for accounting for the fact that there might be something new or unseen in the future. It simply hones in on predicting as well as possible the data that you've observed, and if you don't have a lot of data, or if your data doesn't represent what you think is out there very well, for example, if you only sample from one region within the United States, but you don't sample anything from another region, then you're going to model the region that you sampled from very well, but it might not generalize to the new region well. So maximum likelihood in this case can fail. And so there are many decisions that we have to make. We'll discuss several of these throughout this course. That makes machine learning, in a sense, very much an art as well as a science. And we've gone through one specific example, a simple example here, but in future lectures we'll discuss many more.